Hello and welcome to Project 152, your weekly specialist exam prep. Now, every week we go through past questions from past external exam papers. And now, last week I gave you 5 questions to do. Link in the description if you want to download next week's 5 questions. But this week we're doing the solutions to last week's questions. Click the link, it'll all make sense. Okay, let's get started. First question. Alright, so we're looking at complex numbers here. We have a polynomial and it's being divided by that, and we're being asked what the remainder is. Now, the remainder theorem says that if we sub in I, not negative I, but I, if we sub that in and we figure out what that is, that's what the remainder is going to be. So I'm subbing in positive I for Z, not negative I, positive I. All right, what am I going to get? I cubed minus I squared minus I minus I. Okay, so I've just subbed it all in there. Okay, what's I cubed? That's negative I. Now, I squared is negative 1. So negative 1 times negative I is just positive I. And then I have negative I, and then I have negative I. All right, negative I, positive I, those ones cancel out. I'm left with 2 of these, negative 2I. I believe the answer is A. Alright, now this is not the only way you could have done it. You could have set up like a polynomial division type thing and gone through the whole process of polynomial division, and right down the bottom you would have had a remainder, and that remainder would have been negative 2I. But oh my gosh, this is so much harder than understanding what the remainder theorem is, and that is the remainder theorem. So that's what you should have done. You should feel a little bit of a goose if you've answered it in this way. Alright. Celebrate, and next question. All right, continuing a theme here, we've got complex numbers again, this time sketching subsets. Now, I'm going to approach this by looking at my equation here and letting z equal x plus yi. So what that has the effect of doing is essentially creating a Cartesian equation of whatever my subset is. So everywhere I see z, I'm going to put x plus yi. All right, so magnitude x plus yi, well, that's a bit squeaky, equals magnitude x plus yi. So again, I'm just substituting that z for x plus yi, but then a minus 2 on the end. Okay, so that's it, just x plus y instead of z. Now, if I want to find the magnitude or the modulus of this complex number, it's just Pythagoras' theorem, right? It's just the square root of x squared plus, and be careful here, not yi squared, just y squared. Right, because this is a complex number on an argand diagram. I'm just finding the modulus, so the real component, the imaginary component, don't square the I. All right, is equal to the square root of, now the real parts of this are this and this, so x minus 2 is the real component, right? So x minus 2 squared, squeaky, and then I've got this imaginary component, which is y again, plus y squared. Okay, so what do I have? I have a square root on both sides, so I can get rid of those. So now it's just x squared plus y squared equals x minus 2 squared plus y squared. Okay, easy done. There's a y squared on both sides, so I can cancel those out. So now I'm just left with x squared equals x minus 2 squared. Now, it's going to be very tempting here at this stage to do the wrong thing. Everything under the blue line is going to be wrong. Wrong from here. If you square root both sides, you're going to write like x equals x minus 2, and then like the x's cancel out, and then it's a disaster, right? So you can't do this. Why can't you do this? If you're taking the square root of both sides, the square root of x squared is not x, it's plus or minus x. So you end up with like plus or minus x equals plus or minus x minus 2, and then you've got like 4 cases, and it just becomes really, really horrible. So you can't really square root both sides like this. What you can do though is expand. So you can say x squared equals x squared minus 4x plus 4. And now those x squareds cancel out delightfully, and we're left with 4x equals 4, and x equals 1. So, the equation of this is just x equals 1. Where's x equals 1? here, x equals 1. Perfect. Now, this is your chance to write something in the comments. I've done all of this working here. I love doing it this way. I know that some people can kind of just look at this and know what the answer is. So I'd love to hear if you're that kind of person who can look at this and just know that the answer is that. What's your thought process? What's your reasoning to getting to C here? I'd love to hear about your geometric interpretation of this equation. For now, though, I'm going to celebrate and next question. All right, so here's the next question. And now I'm wondering, is this Unit 3 content or is this Unit 4 content? In any case, I think it's like maths methods content, so we'll be able to solve this easy, straightforward. All right, a particle moves in a straight line with a constant acceleration. Okay, what is that? Constant acceleration, but they don't tell us what the constant acceleration is. So let's just say like a constant acceleration of k. We are actually used to things having constant acceleration because every time you drop something, it has constant acceleration g. All right, which function could represent the particle's displacement? Okay, so let's go from here and say the velocity. Well, the velocity of that is just the integral of this one, which is kt. Now, I filmed a bunch more of this before I realized I have to backtrack. Not just kt, kt plus c. All right, so we don't know anything about this to be able to figure out a c value, so we're just going to have to keep moving forward. All right, the integral of the velocity is going to be our displacement function, and that's going to be the integral of this, which is kt squared over 2, plus that c, but this time like c, like t, right? Because like that was c, now there's a ct, plus d. All right, so this is super strange because now we've got to look at this and say, okay, which of these looks like this? And it's not immediately obvious which of these does look like this, right? But the only one that's got a t squared in it is this b here. Xt equals t squared. All right, now, where did the ct go? Well, if the initial velocity was 0, then ct would not exist. And if the initial displacement was 0, then that d value wouldn't exist either. So we end up with like the displacement function is equal to kt squared over 2. Okay, and then that begs the question, well, hang on, what happened to this k value? Well, for this b to be a possible answer, k, I guess, k would have to equal 2. Because then we'd have 2t squared over 2. We'd have t squared, which is what b is. Now, what's the purpose of this question? Like, the answer is b. What's the purpose of this question? The purpose of this question is for you to understand that if you start with constant acceleration, you're going to end up, when you get to displacement, by having a t squared. That's always the case. You're always going to end up with t squared. So you didn't really have to do all of this stuff. You could just be like, oh, wait, I've done heaps of questions with constant acceleration. Dropped a ball from the sky. It's falling at constant acceleration. The function always ends up at something, something, something with a t squared in it. There's my answer. So all of this work, but really, like, this question is kind of a I know the answer straight away kind of deal. All right, on to the short response. All right, so question 15, we're looking at complex numbers again. This time we're sketching the roots of a complex number on an Argand diagram. Now this one, students don't do well in, right? That's the past thing, so make sure that you're watching this one and paying attention because it is important. Okay, so we've got z cubed equals 1. Now, there are going to be 3 solutions to this, right? Because we're doing a cube root, so there's going to be 3 solutions to it. Now, I know straight away, this is what's called a root of unity. Now, I know straight away that one of the answers is z equals 1. Like, straight away. And, like, just common sense, like, would tell, like, a year 8 student, if z cubed equals 1, a possible answer for z, in fact, the only answer they would know, is z equals 1. 1 cubed equals 1. Okay, so on our little diagram, that's one of our answers. Now there's going to be 3 answers, and they're going to be equally spaced around the circle, right? So starting from here, there's 360 degrees in a circle. So my answers are going to be 120 degrees apart. So there's going to be one answer here There's going to be one answer right here. Okay, that sketch the solutions to z cubed equals 1 on the Argand diagram. I did. You might be looking at thinking you're not doing enough working, like where's all the working? 2 marks. You get 2 marks here. You get 1 mark for knowing that the length of these is 1, and you get 1 mark for equally spacing them around the circle. So 2 marks, I'm done. The next question here, the solutions to z cubed equals 1 can be expressed in the form z equals a plus bi. So in other words, they're in polar form at the moment, or at least they look like they're in polar form, but we can express them in component form as well. Determine the largest possible values of AB. Okay, so we need to think a little bit about this. Now, AB, right, so this one here, we know straight away. What's this value here? Well, this in component form is just 1 plus 0i. All right, so if we test this AB, we get 1 times 0, which is 0. So we're just taking the A, the B value, multiplying them together, and that value is 0. Now, that is not large. It's not even really positive, right? We're trying to determine the largest possible positive value of AB. What about this one here? Well, this one here, I'm not even going to bother calculating, because when I'm looking at this one, I've got a negative real component and a positive imaginary component. So if it has a negative real component and a positive imaginary component, if I multiply those together, I'm going to get a negative answer. So this is not the one I'm looking for. This is not the solution I'm looking for. The solution I'm looking for is here. This has a negative real component and a negative imaginary component. Multiplying them together, I'm going to get a positive answer. I'm going to get a positive answer greater than 0. So this is where my solution is, right there. So let's just circle that one in pink, because that's the one we're going to be dealing with. We know that in polar form, it's got a magnitude of 1, and it's got an angle there of cis, I might just call it like cis negative 120. All right, so working in degrees here, you can work in radians, it doesn't really matter, we're going to get the same place in the end. Now, writing this in component form, it's z cos negative 120 plus sine negative 120 I. All right, and you should know the exact values of cos negative 120 and sine negative 120. All right, so I won't do a bunch of stuff like, drawing standard triangles and things for you. You should know how to do that. You should know how to do that. All right, and the question is like, let's see. Determine the largest possible positive value of AB. All right, so let's multiply A by B here. AB equals negative, let's say 1/2, times negative root 3 on 2. All right, multiplying them together, we get negative 1 times negative root 3, which is just root 3. And then 2 times 2, which is 4. My answer, oh dear, is root 3 on 4. That is the largest possible value of A times B of these 3 solutions. I think the tricky part about this question is just that part B is just a sort of a question that you've never really been asked before. But this happens a lot where you've explained something and then you've got to do it for the first time in an external. So don't be scared of that kind of thing. Just read it, try to pass it, and then just ask yourself how to do it, I guess. All right, that is that one. And last question. All right, and we are complex numbering again. Consider this function. One of the roots is this, and then determine the possible values for A and B such that all remaining roots have an imaginary component. Okay, tricky. What do we have? We have a polynomial of degree 4, and we have an A coefficient, an A coefficient, and a B coefficient. And we're told that A and B are positive, and we're told that they're real. That's good, because if you've got real coefficients in your polynomial, then the conjugate root theorem is in play. What do I mean by that? Well, it says here that one of the roots of PZ is Z is equal to negative I. That means that one of the factors, one of the factors is Z plus I. But because the conjugate root theorem is in play, it means another one of the factors is z minus I. So great, I know so much about this polynomial already. It's degree 4. I know 2 of the factors, which means that, like, you know, it should have 4 factors. So I already know 2 of them. Happy days. Okay, so what I can do now is write that PZ, let's use green here, that PZ is equal to, and I'll rewrite it, but not only do I know that PZ is equal to this, I can also say that it's equal to Z plus I, my first factor, Z minus I, my second factor, and then another unknown factor, which I'll just call like mz squared plus nz plus p, I guess. All right, so that makes sense, right? We've got a quartic, degree 4. We've got one factor, we've got another factor, and there must be 2 other factors, or just one quadratic factor. All right, so then what we're going to end up doing is trying to like equate coefficients. So what I'm going to do is start expanding this, starting with this z plus I, z minus I. Now that should look like something you recognize. It's going to simply be z squared minus I squared, right? And minus I squared is positive 1, because I squared is negative 1, so negative, negative 1, positive 1. If you're not following that, I've expanded this. I've just realized that IZ and negative IZ, they're going to cancel each other out. Z squared plus 1. Okay, and then I have this mz squared plus nz plus p here, like this. Okay, what could I do now, like looking at this? Well, I think I'll just expand this even more, just by like multiplying through all of those. So z squared times mz squared, dot, 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 dot. I don't think you need to watch me do that, but I'm going to do 6 things. This times this, 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 and this times this. Okay, so looking at this straight away, I can start equating some coefficients, right? So I'm looking here, and I'm noticing that 2z to the 4, mz to the 4. This is my only mz to the 4, so that means that m in my equation here is equal to 2. So 2z to the 4. And I can see this other 2 here, like 2z squared, but I'll deal with that in a second. Okay, I've got nz cubed. Now nz cubed, that's az cubed. So I can just say that n is equal to a, right? So az cubed. Now I actually have 2 z squareds here. I have a pz squared and an mz squared. So I can group those, z squared, and then p, but I know what m is. We talked about that. We know that m is 2. So p plus 2 there, and then I have an nz. Now, nz, az, right? So that means that nz must be equal to az. And then I have a p, and that's just b. Okay, I should be able to do something with this. Okay, I see it. I have p plus 2 is equal to z squared, but I know that z squared is equal to 6. So therefore, p is equal to 4, which means that because this was p, b is also equal to 4. Okay, fantastic news, because I now know that b is equal to 4. So the only thing I don't know is a. Okay, so a little bit of like thinking, looking around, figuring things out. What do we have? We know that this is equal to z plus I bracket z minus I bracket mz squared. Now, what's m? M we figured out already. It's 2. So 2z squared plus nz. Now, what was nz? nz cubed. Oh, so n, we found out that n is equal to a. All right, so az plus p. And we just figured out that p is equal to 4. All right. Now, what does the question say? Determine the possible values for a and b. Okay, so b can only ever be 4. So really this question is just like determine the possible values for a such that all remaining roots of pz have an imaginary component. All right, so all remaining roots. So they already told us that one of the roots was like z plus I, or one of the factors was z plus I, one of the roots was minus I. I figured out this one, which also has an imaginary component. Now I need this one to only have imaginary components. So how can I make sure that this quadratic only has imaginary components? Well, we need to think about our quadratic formula. So there's our quadratic formula right there. And the part of our formula that we need is this piece here, the discriminant. So we need the discriminant to be less than 0. Because if the discriminant is less than 0, then the thing under the negative sign there is going to be negative, and that means that the solutions to the quadratic are going to be imaginary. They're not going to be real. So what that all means is that looking at this quadratic, if I sub it into the part under the brackets, I need it to be less than 0. So b squared, so b is a, this is confusing, so a squared minus 4 times a, and a is 2, and c, which is 4. Now that's the part under the root, that's the discriminant. And we need that to be less than 0. So how can it be less than 0? A squared minus 16 minus 32 needs to be less than 0. Now a squared, I'm going to add 32 to both sides. A squared needs to be less than 32. Now we can do a bunch of solving here, but solving like with a inequality, especially a square root, causes problems. Take a look at the hidden little piece of information in our question right here. A is a positive integer. A is a positive integer. So the question is, which positive integers can I sub into here so that it'll be less than 32? Well, A can equal 1, right? Because 1 squared is less than 32. A can equal 2. A can equal 3. A can equal 4. Can A equal 5? Yes, it can. Now, if A was equal to 6, hiding behind there, if A was equal to 6, that means that that would be 36, and 36 is not less than 32. Okay, we are finished. Our final answer to this question, which I'll put in a little box up here somewhere. Final answer, B equals 4, and A equals 1, 2, 3, 4, and 5. What a pretty little final answer there. That is complex numbers and a complex question. That's worth a celebrate. Now that brings us to the end of week 7 of Project 152. Now if you go into the description, you will see the questions for week 8. Now, spoiler alert, this one only has 4 questions in it. And the reason it only has 4 instead of 5 is because one of the questions is going to be incredible. This question appeared in 2020 and it is a monster question. If anyone manages to finish this, like send me an email because it is hectic. Have a try. Catch you next week.